Greetings of the day. I am Dr. Raghuram Mohan Reddy. The course name is Unconventional Machining Process. Today's topic is parameters affecting the quality of laser drilled holes, part 2, belonging to Mechanical Engineering Department. Okay, this is the course learning outcome of the today's topic. Okay, at the end of this session, student will be able to understand parameters affecting the quality of drill holes. Right. Let us discuss non-traditional machining processes. Okay. So before we going to discuss laser beam machining and under that drilling holes and particularly the quality of drilling holes, let us briefly discuss the starting point of this non-traditional machining processes. Okay. Right. So non-traditional machining processes classified into three main categories: mechanical, thermal, chemical and electrochemical. Under mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. In chemical and electrochemical machining, chemical machining, plasma chemical machining, electrochemical machining. Under thermal, electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. So today we are discussing laser beam machining, particularly drilling of holes and its quality of the operation. Okay, right. Now let us briefly discuss the laser drilling capabilities before we discuss the various modules involved in that laser drilling. Okay, right. Hole feature range table. A diameter 0.005 to 1.27 mm. Okay, and larger in trepan. It will be a little larger. Okay, depth 1.7 mm millimeters. Angle 15 to 90 degrees. Taper 5 to 20% hole diameter. Depth to diameter ratio 50 to 1. Drilling depth trepan 6.4 millimeters. Tolerances plus or minus 5 to 20% diameter. Minimum corner radius 0.25 millimeters. So these are the laser drilling capabilities. Okay. Now let us come to the main thing. Parameters affecting the quality of laser drill holes. So mainly laser beam machining quality of holes depends on these 5 things: working material, environment, laser pulse, focusing lens, assist case. Okay, again in working material, type, surface quality, thickness. In environment, humidity, temperature. In laser pulse, pulse shape, frequency, wavelength, beam divergence, duration, energy, traverse modes. In focusing lens, focal length, focal position. These two are the parameters. In assist gas, type, pressure, nozzle, design. So these are the various parameters affecting the quality of laser drill holes. Okay. Now these are the applications. So based on these applications, how the quality of hole will be depends. Okay. So lasers are widely used in many industrial applications, including drilling. So today we are mainly focusing on this drilling. Okay. Next, plating, heat treatment, cladding, alloying, welding, and machining. Okay. Now let us discuss assist gases in the beginning one. Okay. The gas jet is normally directed with the laser beam into the interaction region to remove the molten material from the machining region and obtain a clean cut. Okay. So see here, assist gas, the one of the parameters affecting the quality of laser drill holes. Now the assist gases. Okay, the gas jet is normally directed with the laser beam into the interaction region to remove the molten material from the machining region and obtain a clean cut. Assist gases also shield the lens from the expelled material by setting up a high pressure barrier at the nozzle opening. Okay. Next, pure oxygen causes rapid oxidation and exothermic reactions, causing better process efficiency. Okay, so here pure oxygen causes rapid oxidation and exothermic reactions, okay, causing better process efficiency. So that is the role of assist gas in the quality of making drill hole. Next, the selection of air, oxygen, or an inert gas depends on the workpiece material and thickness. Okay, here the selection of gases or natural air or oxygen or an inert gas depends on the workpiece material and its thickness. An inert gas such as helium or argon should be used if a cut edge of a better quality is required. So basically we use inert gas of helium or argon can be used for the better quality of the hole. Okay, it should be borne in mind that the smaller the diameter of the gas nozzle and the narrower its distance from the workpiece surface, the better is the quality of the cut. Okay, smaller diameter and narrowest distance. Okay, these two cause the better quality of the cut. Next, gas pressure also plays a significant part in the determination of quality and rate of machining. Okay, gas pressure is also one of the important parameters affecting the quality of the drill hole. Okay, right. Next, material properties and environment. These include the surface characteristics such as reflectivity and absorption coefficient of the bulk material. Okay. Additionally, thermal conductivity and diffusivity, density, specific heat, and latent heat are also considered. So these are the material properties and environment related information. Okay. So here what is happening? surface characteristics such as reflectivity and absorption coefficient of the bulk material. Okay. So additionally, thermal conductivity and diffusivity, density, specific heat, latent heat are also considered. In this regard, the minimum laser energy required to vaporize plastic is generally lower than that for metals. The removal rate is enhanced for materials of low thermal conductivity, diffusivity, melting point. So these are the other characteristics which influence the removal rate to enhance. Next, during 1969, Gagillon et al. Used a pulsed ruby laser for piercing holes in diamond wire drawing dies of 1.4 millimeters diameter. Okay, so Gagillon experimented and he has reported that pulsed ruby laser for piercing holes in diamond wire drawing dies of 1.4 diameter. 250 pulses of energy, 2 to 3 joules, duration zero point 0.6 milliseconds, and 1 pulse per second were used to perform an opening of 0.46 millimeters in the die. So that is the report by Gagliano during 1969. In case of drilling with multiple pulses, an aspect ratio of 40:1 for a 0.127 millimeters diameter hole through 12.5 thick material has been reported by Bellows and Coles during 1983. They also found that the depth of holes produced increases initially as the diameter widens. Here it is directly proportional to the diameter of the hole. Okay, so depth of holes produced increases initially in the diameter widens up to a limit beyond which the penetration depth decreases. After certain limit, it starts decreasing. Okay, depth of hole initially increases along with the diameter of the hole. So later on, it will be decreasing. Okay. Next, they draw attention to small hole drilling applications such as fuel filters, carburetor nozzles, and jet engine blades cooling holes. Okay, so all these are basically automobile engineering applications: fuel filters, carburetor nozzles, and jet engine blade cooling holes. Okay, right, right. A neodymium doped yttrium aluminum garnet, that is NdYAG. Okay, in simple it is NdYAG. Yttrium aluminum garnet, YAG. Yttrium aluminum garnet. Okay, so Nd means neodymium doped. Neodymium doped. Okay, so NdYAG laser fitted with CNC, computer numerical control, on 5 independent axes for positioning component weighing up to 1 kg has been used in the aircraft engine industry by Korf during 1983. So Korf researched that with NdYAG laser fitted with CNC on 5 independent axes for positioning component weighing up to 1 kg has been used in the aircraft engine industry. Okay. Accordingly, holes in gas turbine components and nozzle guide vanes 8 mm long and with an aspect ratio of 10:1 were produced, thus realizing savings of 20 to 30% over EDM. Okay, so here figure 3 shows laser drilling cooling holes in a turbine vane. So you can visualize very small tiny holes on the turbine vane. Okay, cooling holes in turbine vane by course during 1983. Okay, so here the quality is very essential for the purpose of operating this turbine blades. Okay, so there should not be any deviation or no tolerance will be accepted, so that we have to make the holes as per the design specifications. So for this we have to go with laser beam machining, okay, with high quality holes. Next, Bohme during 1983 pointed out that pulsed solid state lasers produce hole diameters between zero point 0.1 and zero point 0.5 millimeters at a rate of 0.1 to 10 holes per second. The depth to diameter ratio lying in the range 1:1 to 10:1. Okay, so all these are numericals that we can understand. Nothing is required again. But here the important one is that, see here, zero point 0.1 to 10 holes per second. Okay, so these many holes that we can make in 1 second. Okay, with the diameter 0.1 to 0.5 millimeters. Okay, during laser hole drilling, optical pumping arises from the internal reflections of laser light as the hole becomes progressively deeper. Okay, during laser hole drilling, optical pumping arises from the internal reflections of laser light as the hole becomes progressively deeper. Right. The maximum hole depth achievable is therefore diminished by the energy lost due to reflection from the hole wall and also by the decrease of the hole aperture. Okay, so here the maximum hole depth achievable is therefore diminished by the energy lost due to reflection from the hole wall and also by the decrease of the hole aperture. Okay, right. Another detrimental effect to laser machining is the production of plume vapor within the cavity that absorbs laser energy. As a result, a shallower hole is produced. Okay, see here a shallower hole will be the result because of the cavity. Okay, and plume vapor. Okay, next, under such circumstances, repeated pulses are recommended by Megoff during 1988 to overcome such process limitations. Okay, so here shallower hole will be producing. So in order to overcome that problem, what should we do? Repeated pulses. Okay, so recommended by Megoff. Okay, so these repeated pulses reduce the or eliminate the shallower hole production. The problems of limited maximum hole depth, non-cylindrical profile, and the presence of excessive recast material are normally associated with conventional lasers. Okay, the problems of limited maximum hole depth, non-cylindrical profile, and the presence of excessive recast material are normally associated with conventional lasers. Lau et al. During 1994 introduced the ultrasonic assisted laser machining technique not only to increase the hole depth but also to improve the quality of holes produced in aluminum based matrix composites. Okay, so here metal matrix composites with aluminum. So here the focus is on not only towards the depth of the hole but also for the quality of the hole production. Lau et al. During 1994 introduced the ultrasonic assisted laser machining technique. Okay, using such method, the hole depth was increased by 20% in addition to the reduced degree of hole tapering. Okay, powers, cutting and grooving. So under this, powers in the range of 200 watts to 1 kilowatt are recommended for cutting through steel. Okay, oxygen jet assistance is found to be suitable for most metals as the gas liberates additional energy by the exothermal chemical reactions occurring in the machining region. Okay, so under cutting and grooving, powers should be in the range of 200 watts to 1 kilowatt are recommended, and oxygen jet assistance is found to be suitable for most metals as the gas liberates additional energy by the exothermal chemical reactions occurring in the machining region. Next, Bohme during 1983 described the use of 500 watts CO2 laser in conjunction with a computer numerical control system, that is CNC, for cutting steel plates of thickness up to 5 mm. Okay. Accordingly, the cutting speed has been found to decrease with an increase in the workpiece thickness. So these are inversely proportional. Okay. So here the cutting speed has been found to decrease with an increase in the workpiece thickness. Okay. So speed will be decreasing with the increase of the workpiece thickness. So these two are inversely proportional. Okay, right. Next, CNC, computer numerical control. Laser cutting has also been used in the production of clothes. Accordingly, a system incorporating 400 watts laser beam guided by mobile mirrors is used to cut a 2 meters wide moving fabric at a rate of 80 meters per minute. So particularly in clothes industry, we are using computer numerical control setup laser cutting machine. Okay. The required styles are held in the memory bank of the computer. Okay. So based on that designs, whatever it may be, the sketch in the memory that will be reproducing onto the cloth. Okay, right. Cutting of flat quartz of thickness 5 to 100 mm has also been performed by traversing 100 to 250 watts continuous output CO2 and to helium laser focused to a diameter of 25 to 100 micrometers across the material. Okay, so here thickness range cutting of flat quartz of thickness 5 to 100 millimeters. Okay, with a power range 100 to 250 watts. So here the gas is CO2 and to helium. Okay, that is the laser gas. Okay, focused to a diameter of 25 to 100 micrometers. Okay, across the material. Furthermore, Markov during 1988 reported that a 300 watts laser beam of the same type can be used to cut through 3.1 millimeter thick steel plate at 1.02 millimeters per minute, leaving a heat affected layer of 0.5 millimeters width. Okay, so here the objective is to cut the material without any heat affecting zones. So if there is any heat affecting zone, the residual stresses will be formed. Okay, so however, we have to focus on all these side effects also during the machining or cutting. Okay, right. Laser cutting of electrical sheets offered an alternative machining method that avoids the high wear of conventional cutting tools, mainly caused by the high silica content, that is 1.4 percentage of the material. Okay, so this is regarding electrical sheets, okay, which are offering an alternative machining method that avoids the high wear of conventional cutting tools, mainly caused by high silica content, that is 1.4 percentage of the material. The high flexibility of a computer numerical control laser workstation in combination with a CAD CAM system, computer aided design and computer aided manufacturing system, gave the advantage of the prototype at short run production of sheet blanks of complex geometry such as rotor and stator blanks. So these profiles are very complex. So we can cut by using this laser workstations only. It cannot be machined with conventional machining process. Okay. Using such a method, laser cutting of electrical sheets became possible at high speeds of 8 meters per minute when using a 500 watts CO2 laser and 0.65 thick sheet with an excellent cut quality. So here the importance of this information is that how much power is best suited and at what rate or speed that it can be operated and to what thickness that it is best suited. See here 0.65 thickness sheets. Okay, so if the thickness is above that one, then we have to change the speed and power also. Okay, so based on these research empirical relations or information, we can get the quality of cutting our holes. Next, fiber composites are sensitive to conventional cutting and drilling due to their inhomogeneous and anisotropic nature. Okay, inhomogeneous and anisotropic nature. Okay, so delaminating, splintering, the presence of blurs, and short tool life caused by the abrasive nature of the fibers are typical problems. Okay, what are those? Delaminating. Delaminating means it is exactly opposite to the sticking or some lamination. Okay, so spalling is also one of the synonym to this delamination. Okay, next, splintering, the presence of burrs and short tool life caused by the abrasive nature of the fibers are typical problems here. In laser cutting of composites, the effect of material anisotropy such as the fiber arrangement is of less importance. Okay. Next, Lau et al. During 1990 used NDR laser for cutting carbon fiber composite materials as faster rates than the EDM, electron discharge machining, and the cut surface is less homogeneous. Okay. Next, compressed air assistance provided a large depth of cut than organ. Okay, so basically inert gases would be better, but here compressed air assistance provided a larger depth of cut than argon. Okay, however, argon gave smooth and less thermal damage to the cuts. Okay, but compressed air is provided larger depth of cuts, but here smoothness is very much required. So we better go with argon. Okay, when there is a requirement of smooth and there should not be any thermal damage, then we have to go with argon gas. Okay, they added the fiber orientation affected the depth of cut besides the width of the heat affected zone. Okay, standard oxygen assisted laser cutting of stainless steel sheets does not provide satisfactory performance. Okay, so this will not give any satisfactory performance. The oxide dross that clings to the bottom edges of the cut forms a hard bar, thus limiting the thickness to be cut by 3 millimeters. For machining of larger thickness, the machining speed is consequently lowered and the finished edge is similar to an oxyacetylene flame cut. Okay, so this whole information will be used for the better cutting edges, maybe at bottom or maybe in any corner. Okay, the main obstacles in laser machining of stainless steel are due to the low fluidity of the melt and partially the high melting point of chromium oxide Cr2O3 that also restrains oxygen diffusion in the molten cutting front. Okay, so this is very good information here. So in order to solve the problems associated with laser cutting of stainless steel, HSU and Moylan during 1995 developed a laser machining technique that employs dual gas jets, okay, here shown in this figure, to remove the viscous stays in the molten cutting front and thereby allowing stainless steel to be cut faster, cleaner and thicker. Okay, so here the figure giving information here, it is the film thickness. Okay, so this is coaxial O2 nozzle here and off axial O2 nozzle setup here, and O2 will strike here, and this is impinging angle. So here the ray pointing onto this workpiece. Okay, right. So the film thickness can be this one. Right. For a better understanding of process behavior and to achieve and maintain high quality machining process, developments in the area of monitoring, diagnosis, regulations, and modeling become essential. Okay, so in order to better understanding, we have to go with all these regulations, monitoring, and modeling. Okay, so in this regard, Ilbas during 1996 studied the formation of stress by monitoring the high emission from the upper surface of the workpiece during laser cutting using fiber optic cable and a fast response photodetector. Okay, right. Recently, Ueda et al. During 1997 and Spar et al. During 1997 investigated the temperature of workpiece radiated with carbon dioxide CO2, okay, pulsed laser in order to determine suitable conditions for cleavage cutting of brittle materials in an attempt to control the heat conduction in the workpiece material during laser cooling. Okay, so during 1993, Chrysolines adopted the use of a water jet in tandem with the laser beam, thus reducing the heat affected zone by 50%. So here, the main important point is heat affected zone. While we are machining, that is cutting, the heat will affect the nearby zone. That is nothing but heat affected zone. If that it affects, the residual stresses will be found later that it will impact in the structure of the material in later stages during the operation. So we have to reduce that heat affected zone. So here the heat affected zone is reduced by 70%. Like these are the various references associated to this topic, and thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.